Okay, welcome to our 6.3 lesson on isolated and non-isolated systems, and we're looking at mechanical energy in these systems again. So the first thing that we need to define is what is an isolated system. Um, the example given in the textbook talks about how in an isolated room, the total amount of money in the room before and after a transaction is constant. Another way to think of it, an isolated system, is that whatever is happening in there, that no change is going to come in or out. Whatever was there will always be there. So let's get that in here. Can come in or out of a system. That doesn't say that change can't happen within the system, but nothing's going to go in or out. Whatever the energy that you started with is going to be the energy that you leave with. We also make some assumptions when we talk about isolated systems. We assume that these, in physics specifically, that they're isolated from all other objects in the universe. And this is a big one, in isolated systems, we also assume frictionless. So always keep that in mind when we're dealing with things here. Frictionless. Now, like I kind of suggested at the top here, an isolated system means that things can occur of change within the system, but they're not going to go in or out. So that's where the conservation of energy law comes in. So it's simply that energy may be transferred, in or out. Sorry, not in or out, from one object to another. From one object to another, or transformed. And that's when we talked about like how things change from kinetic to potential. And you're going to think this is really similar to what I just said with the isolated system, but this is kind of the law of it. Now, we also have a relationship between that kinetic and potential energy in the isolated system. And again, I already kind of hinted at it, that we know that can be transformed. Like the example in one of our test questions was you're skiing down a mountain. Like, how does that relate to the change and transference of energy? So, this law of conservation is a fundamental principle of science, and it's super useful for analysis and prediction of the objects within these systems. And it states, in terms of mechanical energy, any gain in kinetic energy must be accompanied by an equal loss in potential energy. So, in terms of mechanical energy, any gain in kinetic energy must be accompanied, must be accompanied by an equal loss of potential energy. And that makes sense. That's, again, all those different equilibrium laws that we've been studying. Now, when we're talking about that conservation of mechanical energy, it's very simply like if I had to put a formula to it, it's just EM1 is equal to EM2. But when we're talking about this, if I needed to put like another thing to this, it's really just the change in the kinetic energy. That's how I've been taught how to write it. That's why I keep writing it wrong for you guys. So it's EK is equal to the change in the potential energy. Kind of the shorthand of it. Now, if we are thinking about energy versus position for a block that's sliding down an inclined plane, this block is sliding down a frictionless inclined plane. The gravitational potential energy, the EP, is going to decrease. And then as that EP decreases, that EK increases proportionally and at the same rate. And then at any time when we add these together, it's going to equal the block's mechanical energy. And because of the way this is added, and we know that these lines are perpendicular to each other, so we can use some good old Foundations 10 math, that when we sum these guys up, we're going to have a constant mechanical energy. So no slope change. And what that tells us is that, again, that this EK equaling to the negative EP, this is just another graph way of seeing it, is that the energy is conserved. Conserved. So let's jump into an example. We have a frictionless roller coaster car. What a world that would be. Has a mass of 8.00 times 10 to the 2 kilograms. At one point on its journey, the car has a speed of 4 meters per second and is 35 meters above the ground. Later, its speed is measured to be 20 meters per second. So we have a height, we have a mass, and we have two different speeds. We need to calculate its total initial mechanical energy relative to the ground. So, mechanical energy and as we just saw in this graph is that at any point in the system, we are going to get the same additive energy because the mechanical energy in a frictionless isolated system is going to be the same. So that's why it doesn't really matter. When I set this up, this is going to be mass velocity squared divided by 2 plus mg, and then 35 meters above the ground relative to the ground. Change in height is really just going to be that 35 meters, but I digress. So we have 8 times 10 to the 2 kilograms multiplied by 4 meters per second squared, all divided by 2, plus the same mass, multiplied by gravity, multiplied by height. And I thought I had enough room, but I don't, and that's fine. Close enough. And then when I calculate this all together, I get 2.81 times 10 to the 5 joules. And then it wants to know the gravitational potential in the second instance. So when I'm saying the second instance, I'm worried about that second speed that I'm using. So we know that it's going to be constant at no matter what stage that we put it at. So that's important to remember that because this value is going to come into play here. But because what I'm trying to find is my EP2, so the potential energy at the second point, let's rewrite this EM2. So the kinetic energy at the second instance plus the potential gravitational energy at the second instance is equal to the mechanical energy at the first instance. So it's again like that one question we did in the last video where we're setting up two parts to be equal to each other. So let's throw some stuff together here. I'm gonna make sure to subtract this over because what I'm trying to solve for is this EP. So then this is EP2 is equal to EM1 minus EK2. So this is going to be that MvO2 squared. So we're going to have 2.81 times 10 to the 5 joules minus 8.00 times 10 to the 2 kilograms multiplied by 20.0 meters per second squared, all divided by 2, which gives us 1.21 times 10 to the 5 joules. So that tells us, just to kind of explain what's happening here, is that as in this second instance, at 20 meters per second, our gravitational potential energy is 1.21 times 10 to the 5 joules. Our kinetic energy changed, and our gravitational potential energy changed. It went down. So as the kinetic energy increases, the potential energy decreases. And you can see that more clearly if you break down these points that are happening here. So like those intermediary calculations. That's okay. Next we have a pendulum. This is a simple pendulum. Simple pendulum. So this is an excellent approximation of an isolated system, and it's because what this is doing is it's just a simple pendulum that is working with Earth's gravity. So Earth's gravity does work on this pendulum to transfer the potential energy into the kinetic energy. EP into kinetic energy. And on the upswing, so this is on the downswing. On the upswing, it changes it from kinetic energy back into potential energy, so it just kind of swaps places there. This plays in with Newton's third law, and that's that law where it's every action, there's an equal and opposite reaction. This means that the Earth's gravity acting on this pendulum, converting gravitational into kinetic, the pendulum is also going to have to do the opposite. So the Earth is part of that isolated system, but because the Earth is so huge and the pendulum is so small, we don't really have to kind of worry about how the Earth is going to react to it. We just basically ignore the effects of the pendulum on Earth, and we just look at this pendulum like it's an isolated system. And this is just like another good graph that explains like how the mechanical energy is constant. So it doesn't matter at what instance you do that adding, it's just going to work the way that we need it to. We got a good example here, an ideal pendulum, as shown in figure 6.32. That is which one here? Oh, sorry, that is a simple ideal pendulum. Means the same thing. Is suspended by a string that is 2 meters long. That is a very long pendulum. It is pulled sideways and released at its highest point of the swing. The pendulum bob is 25 centimeters above the floor. At the lowest point, the swing is 5 centimeters above the floor. The mass of the pendulum bob is 250 grams. Let's start with A. At the highest point, what is the mechanical energy? So when we're at our highest point, we have to remember speed is equal to 0. It's a key thing to kind of remember here. I should switch back to a nicer color. So for A, what we are looking at here is we have our mechanical energy is equal to our EP plus EK. Now something really fun is going to happen here, but let's write out our little formulas, and you'll probably see what's going to happen right away here. Because what happens when our speed is 0? Well, we don't really have to worry about what's happening here. So then we're going to have our mass. This is in grams. This needs to be converted to kilograms by dividing it by 1,000. So then we have 0.250 kilograms multiplied by our gravitational constant multiplied by our height. So the highest point above the floor. So 25 centimeters and 2 centimeters. So we should get above the floor 2 meters long. And at its lowest point is 5 centimeters above the floor. So that gives us our height in meters here. This should be 0.250 meters. And then this is 0.050 meters. So many extra zeros there. Okay, so then our height changes to 0.250 meters, which gives us in newtons, because it's kilograms, joules, because it's kilograms meters squared, meters times a meter, centimeter squared, which gives us 0.613 joules. Now I'm a little concerned that I'm going to run out of space here. I wonder if I can make these smaller. No, but I will deal with that later. So B, what is the mechanical energy of the pendulum relative to the floor when the bob is at its lowest point? Well, in an isolated system, mechanical energy is constant, so it's the same. And you can say that at its second point, because no matter what, it's going to be the same. What is the kinetic energy of the bob at its lowest point? Well, that's going to require a little bit more work. I'm going to run out of room. So if you need to write this down, pause the video, but what I'm going to do is I'm going to erase this so I can come back to it. This means that the filled in notes won't be quite as useful. You never know how big you're going to write. That's what I know. Okay, so then C, the kinetic energy at this point, we talked about EM2 being this mechanical energy 2, still equal to its potential energy plus its kinetic energy. And we're solving for that kinetic energy. So that's when we're going to rewrite it and reset it. So it looks like this. We know what our EM2 is. We just calculated that. 613 joules minus the potential energy at that point. Which is going to give us 0.491 joules. and then it wants the speed at its lowest point. So we did something very similar to this last day. I'm going to use purple here just to kind of differentiate the two parts of the question. And I told you guys it probably wouldn't be a bad idea to have this kind of always written down somewhere because of how often we're going to have to use it to solve for velocity. So if you need to know how that's worked out, go check one of the other videos. But this one, as we rewrite it, we know it looks like this. So then our velocity is equal to the square root of 2 multiplied by 0.491 divided by our mass of 0.250, which gives us 1.98 meters per second. And like I said, if you needed the other two parts, the A and the B, please take your time and go back. You guys might be able to write a little bit better and get this a little bit over. The last thing that we need to look at is conservative and non-conservative forces. So when we talk about conservative forces, what we're saying there is a conservative force is it's forces that act within the system without affecting it, the mechanical energy. Not going to say something. It's a force. So examples of that would be gravitational for us. And for others, the other one would be our elastic. E-L-A stick. And a key thing that we need to know is that friction is a non-conservative force. So because friction is a non-conservative force, what we need to worry about here is how mechanical energy and friction kind of work together. And there's a lot that we could go through here in order to kind of explain what's going to happen with mechanical energy and friction, but let's kind of keep it a little bit simple for us. In any system, if there is friction, any motion of an object is subject to it. When we look at the work done by friction, what we've seen before is that the length of a path will affect it, not necessarily the height, but like how long a ramp is versus how high a ramp is, which sounds silly to kind of talk about the difference, but that was definitely something that we brought up even today. And when we talk about this, like if we think about the work of friction equaling to the force of friction multiplied by the displacement, the distance, we have to think about like how this works together here. When we are looking at work done, we're always looking at how much it takes to overcome the force of friction. So I'm trying to think of the best way that I want to say this. It's going to cause the amount of mechanical energy to change. So the mechanical energy changes. So that our mechanical energy is equal to the work done by the force of friction. Is going to equal this change in mechanical energy. Actually, that's probably not where I should put it, hey. Let's just kind of block this off. And that's just talking about work and work done. So then when we kind of look at this, when we have this change of mechanical energy, change of mechanical energy is our EM2 minus our EM1 is equal to our work of friction. Now, our work and force of friction is always done directly opposite to the motion. Like if we drew out like a force diagram, we know that work of friction or force of friction is always done in the opposite way, and that's assuming that this is positive and this is negative, and it's opposite of the direction that we're going. So our WF value, the calculated value, is always going to be negative. And that the friction is always going to reduce the mechanical energy. And that makes sense. Like mathematically, we talked about that some things just make sense mathematically of why they should be negative. And then the last thing is talking about this energy versus position for a non-isolated system. And you can kind of see how that works. When we were talking about the prior one, you could see that the line was constant. This line has a slope, which means that there is a change that is happening. And that's just another way to sum it up. Or we can also work around the idea of what the change, like how this works. And it's very simply like the change of energy is equal to the force multiplied by the delta D. So if we're trying to find that EM, the F, this is rearranging the definition of work, the friction, and stuff like that. So then we can see that it's the change of the energy, change in distance. So these are all of the energies coming together, and this is over the change of distance. So it's like saying the change in y over the change in x for that kind of math-minded that we're doing there. So I hope that helps. You guys have several more comprehension questions than you're used to, but it's just because they don't have numbers in them that I call them comprehension questions. And then you have a few application questions that work alongside all the stuff that we did today. If you have any questions, please let me know. Past that, good luck.